Hi everyone, today I'm going to show you one of the tasks that I encountered like a few months ago when I was preparing for the second stage of Polish Olympiad in informatics. And I found this task like really entertaining and a little bit tricky. But I think that it is worth I thought that it was worth to create a YouTube video with like this task statement and with my solution to this task. Because only like 40% of people in szkopul solved it. So, but it's not really hard in my opinion. So I think that I also think that I have like a simple solution. But later we will go on to that. Right now I won't like read this statement because it's too long. I will like explain it in my own words. So what do we have? We like have some trains, like n trains, where n is less or equal to 1000. Every train has length L, which is less or equal to 100. And we have some m queries, and m is less or equal to 10,000,000. And what is our goal? And what are these updates? In each of the update, we choose like the letter from the as we can see, we have like four numbers, yes, A, B, C, D. So we choose a letter from train number A on position number 3. Yes, so in this example, it will be this letter, B. And also we take a letter from train number 5 on position number 4. So it would be letter A. And we simply swap them. Yes, so after swap operation, on this position we will have letter A, and on this operation we will have letter B. And what is our goal? Our goal is to calculate for every train, yes, for every train, after performing some number of like swapping updates, what is the maximum number of other trains, including also our train, so the result is logically at least equal to 1, which are the same as us, yes? And the same, I mean that like these strings, yes, are identical. So, for example, we have string AA and another string AA, so they are identical, yes. Okay, so we can also like I can also explain it to you on this example. So we will focus on train number 1, which is on track 1, as was mentioned in the statement. Sorry. So we have in the beginning we have ABA BBD, and we can see that before any updates, yes, there is no other train which is the same as us. Yes, there is simply not other train. Yes, after the first update, we see that like after swapping this, where I told you like there was the swap between second and fifth train. Yes, so after this swapping, the second train became the same as the first train. So here in the first, after performing one update, our result for train number 1 is 2. Yes, and then we will like proceed with the next operations, etc. And our optimal solution for like the train number 1 is after phase number 4, because we can see that we have string AAABBD, and string, the second string is also AAABBD, and also string number 3 is the same as previous ones, but string number 4 is CABBBD, which is completely other than these third three ones, three first, yes, and the same situation is with this last string, yes. So we have to calculate such a number for every train, yes, and we have to output the optimal result. So okay, I have here some examples, and I will present to you 3 solutions. Yes, we will start with like the slowest solutions, which works in n square times m. And what do we do in this task, we will, in this solution, we will simply iterate through every string. Yes, so we'll begin with this string, then we'll proceed with this string, and so on. Yes, so we'll that's why we have in our complexity n. For every string, we will calculate. We will go through every phase. Yes, so we will start with phase sum 0, then phase 1, phase 2, phase 3, phase 4. Yes, and after performing some prefix of phrases, we will calculate again through every string. Yes, to calculate how many other strings are the same as us. Yes, and yeah, so our final complexity of this solution is n squared times m. Yeah, I think so. It is like that. Maybe also only. Yes, if we also are sloppy with our implementation, we can also have something like times L square, yes, or maybe only L, where the L is like the length of these strings. But if we are not sloppy, then this should be our complexity. Okay, so this is for the first solution. The second solution is without the square in M. And how do we do that? We simply eliminate like the third loop, the loop where we are counting how many strings after performing some prefix of operations are the same as our if string. Yes, for example, we are in this string, yes, and we have to know after performing some prefixes of changes how many other strings are the same, and we can simply use hashing method. Yes, hashing and then counting sort. Yes, so for every hash we'll store like the value which will represent the number of like the same string, so it is equivalent to the same hash values. And I will swiftly write the formula for hashes, which is commonly used in competitive programming. So it is Si times PY and mod some number m. Okay, so Si is simply the if character in the string. Pi is some prime number which has to be obviously greater than the ASCII character of Z, because Z is last character of the alphabet. I oftenly use 199, yes. And it is also advisable to use prime numbers, yes, because there is smaller probability that our hashes will collide. And m is also some big integer, yes, and it also has to be a prime number. Yes, I often use 10 to the power of 9 plus 7. And this is the result for some index e. Then we'll also calculate formula, recursive formula f plus equal f from I minus 1. Yes, and when in our recursion we get to the I equal to 1, we stop the recursion and we return our results. Yes. So that's how we can swiftly and smoothly change our strings into the numbers. Yes. So that's the solution which works in n plus m. And now I will show you my elegant solution which will work in much faster time. And so what do I do? for every hash, yes, I will store a vector, yes, and in the vector, I will store three informations. First information will be like some times, like time of entrance or exit. Later on, I will explain what does it mean in this context. So this is like first information. Second information is, and they can simply be our like indices, yes. So we don't really have to store them. Second type of information will be the number of train. Yes, so for example, train number 1, train number 2, 5. I don't know, train number 2, and train number 1. Yes. And third type of information will be like it will be like a Boolean array, and each element will tell me if like 1 is entering this vector or if 1 is exiting this vector. Okay, so here it is entering, so 1, which is equal to true mainly, simply, and 0, which is equal to false, because there it will exit. And what is this idea with with entering and exiting? So we simply see that we will perform some these operations. Yes, we will perform this operation, then we will perform this operation, this operation, this operation, and each of these operations we can do like change hashes in odd 1. Yes. Okay, so after performing each of these situations, when, for example, like let's assume that we are considering like vector in the hash z, so hash set z, yes, hash z, and like so in hash z we start in the phase 0, so before any changes we know that train number 1 has this hash, yes, and it will like stay here, stay here, stay here, and in and later in some operation, yes, it will change into another hash. Some, for example, hash number, I don't know, hash with number x, yes. So it will exit our hash z, yes, and it will like, okay, so this is our z. We have their storage for x, and it will like, okay, so I will swiftly rewrite it. Okay, so here we have some elements. It doesn't really bother us, but here, if it's like, I will delete it. If it exits here, yes, and it will now have a value x, so it will enter here, yes. So time 4 corresponds to like the moment of the vector, yes, in which this specific number entered this vector or exited this vector. Yes, and exited, I mean that the value of hash of this train is no longer z, yes. And also we will, I forgot, we'll also have fourth information, and this information will tell us, okay, how many other trains, how many different trains are right now on our vector, yes. So here we have 1 element, then we have 2 elements, 3 elements, and now we see that like this is the even occurrence of these 2, because we can also see that if the occurrence is even, it has to exit. If occurrence is odd, it has to enter. Yes, so if the occurrence is even, so from that also you can see that we don't have to really store this array, but yeah. So it exits here. So now we have 2 elements on the which has the same hash, and then we have only 1 element, because 1 is also like even occurrence of 1. And okay, so we see that on this like consecutive times, yes, one had this hash, yes, had hash z, because we are analyzing hash z right now. So in my opinion, like the optimal number, like optimal result for train number one in hash z, yes, is in this interval, yes, because in the middle of this interval, yes, some new trains were entering the stage, like were given this hash z, and some were leaving this hash z, right? And it was between our time when we were there. So when we will analyze like these like values, yes. So 1, then 2, then 5, and it goes on. When we will reach like the even occurrence of some number, so there is an even occurrence of 1, we will simply check the maximum value on this interval, yes. And how can we fastly like check the maximum value on some interval? We can do it using segment tree, yes, in O odd O from log n. Because we will like each value we will update in our tree, like this the point operation, and then we will use the interval operation, so we also don't have to use lazy propagation here. So it's really elegant. Okay, and when we get this maximum value on this interval, we update our maximum value in our array, because we will have some array with like maximum values for each train, yes. And after these updates, we will simply like output our results, yes. Okay, so one could ask what is the complexity of it, because it could be a little bit tricky. But okay, like we have this observation that the sum of these numbers on all of these hashes, yes, like sorry, like the length of all of these all of these arrays are less or equal 4m plus n. And why is that? So we see that in the beginning we have n hashes, yes, so n beginning states, and for m, because when we have some hash 1 and some hash 2, yes, and we swap letters between them, we get new hash 3 and hash 4, yes. There is also this thing that we can have swaps like in the one train, yes. Okay, I will formally like write it. We can simply have that a is equal to c, yes, where a and c are our numbers from our queries. Yeah, so we see that we can simply go through our map of vectors through every element. We know that this is the like the number doesn't like it is less or equal than 4m plus n, and for every element we will do update or query on our range tree, yes. So our final time complexity would be m times log n. I didn't write this like fixed values and this n because n is relatively small to our m, yes. If we check our yes, our constraints. And so yeah, and this is our final solution. I think this solution is very elegant, I would say. Like and like the method of like storing these informations in map, like on vectors which are on maps and which are also hashed. I think like it's really innovative. I mean, in this task it was the first time when I came up with this solution and I used it. So yeah, I think that it's really really good thing, yeah. And also there is like my code to this task. I will fastly like go through it and analyze everything. So we begin with like these magic lines, which are known known to competitive programmers. So yeah, they simply cut our times. So yeah, they are everybody in some professional level knows them. So okay, there we input our values. There we calculate our powers. There we input our strings and we calculate our hashes. Yes, from this formula which I used before. There we push back our indices on map. We calculate some other values. It's not important. Okay, and then we have these queries, and also we recalculate these hashes. As I said, we can have 4 other hashes. Yes, so we add 4 different indices on our maps, and then we go through map. Yes, as I said, I use here this Boolean array, but it wasn't really necessary. I also use this like counter variable, yes, which tells me how many active trains are there on vectors, and then I simply like updated it in our in my range tree. Yes, there is like my update and query. So yeah, there are also these values to like okay, this is like the limit for arrays, limits for arrays. There are these values for hashes. Oh, like for p-value I used 601, but this is still prime, so it's fine. Yes, there I have my warm-up. And then I go through, yes, if my Boolean value is true, then I ask for this value on interval. Yes, I maximize my result, and then I go on. This loop refers to the situation where we get some hash for some train, but then it doesn't exit the hash, yes? So I also have to calculate like this with the size of an array, yes? There I simply used base minus 1 because it was like the most convenient way to do it. And in this loop I am just cleaning the values, yes? So there will be no trashes in the next iteration. And then simply I output my results, and to be honest, that's all. Okay, so like, thank you. I mean, if you want to check out this task and do it by yourself, it is from 15 Polish Olympiad in informatics, yes, szkopul.edu.pl, and it was from second stage. I don't know if it is hard, but I think that I believe that if this task would be on the final stage, not many people would still do it, yes. Even if it would be on the final stage, I think that it could be like the hardest one from the second stage, or maybe like medium level. So thank you and see you next time.